Hello, and welcome to the Academy of Useless Ideas. Today we are diving in the nested interval property, yet another delightful consequence of the least upper bound property of the real numbers. Picture an ordered set with a collection of bounded, closed intervals. That's a set of points that are greater than or equal to A and smaller than or equal to B. Now, let's say that we have a countable collection of intervals, creatively labeled I0, I1, and so on until infinity, that are said to be nested if each interval contains its successor. Think of it as a set of Russian dolls, but instead of dolls, we have intervals. The nested interval property states that the intersection of these nested non-empty closed intervals is not empty. In other words, there is a magical element that belongs to all of the intervals. So, why is the nested interval property important, you ask? Well, besides giving you a conversation starter for your next math-themed dinner party, it's actually a clever way of identifying holes in an ordered set. If you recall, we previously identified holes in the rational numbers by finding sets without a supremum. However, we can also use the nested interval property to identify these elusive holes. Imagine we have a chain of nested intervals with lengths that tend to 0, where each interval encloses the hole. In this case, since the hole isn't actually part of the set, the intersection of these nested intervals would be empty. It's like playing a game of spot the hole, but instead of looking for something missing, you are identifying its surroundings. Let's get down to business and construct some nested intervals, shall we? To kick things off, let's set the first interval, I0, to the closed interval between 1 and 2. Now, let's use a bit of mathematical magic to construct the next interval in plus 1, based on the previous interval in, using the formula 2an plus 2 divided by an plus 2 and 2bn plus 2 divided by bn plus 2, where an and bn are the endpoints of in. Through the principle of induction, we can prove that these intervals are not only nested, but also not empty. This can be attributed to the fact that if we take a positive rational number q and plug it into the formula, the resulting number p, 2q plus 2 divided by q plus 2, is rational and closer to the square root of 2. While this fact is fairly easy to verify, it does require a bit of creativity to arrive to the formula for p. Now, in the realm of real numbers, the intersection of these nested intervals contains only one element, the square root of 2. However, in the world of the rational numbers, the intersection of these intervals is empty. In other words, by using nested intervals, we were able to capture and identify the holes in the rational numbers. It's like we've equipped ourselves with the ultimate hole detecting tool. The previous example serves as evidence that the rational numbers do not satisfy the nested interval property. On the flip side, we expect the real numbers to satisfy the property since they don't have any holes. However, we can't rely solely on our intuition to prove this fact. Instead, we need to produce a rigorous proof. Given that the defining difference between the rational and the reals is the least upper bound property, we must utilize this property to prove that the real numbers satisfy the nested interval property. Our strategy involves finding the supremum of all the left endpoints of the intervals and demonstrating that the supremum belongs to the intersection of the nested intervals. With this proof, we can rest easy knowing that the real numbers live up to our expectations and have yet another impressive property to their name. Consider the sequence of non-empty bounded nested intervals in. We can describe each interval by its endpoints an and bn, since in is not empty. Given that the intervals are nested, every an is less than or equal to its successor an plus 1, while every bn is greater than or equal to its successor bn plus 1. It is important to note that if m is larger than n, then bn is greater than bm, which is greater than am, which is greater than ak for every k smaller than n. This means that any arbitrary right endpoint Pn is an upper bound to all the left points An. Therefore, the set A of let points is upper bounded and has a supremum alpha. Now we need to verify that alpha is in every interval. To do so, we need to prove that alpha is greater than every An and less than every Bn. We know that alpha is larger than every An because it is an upper bound of A. Additionally, since every Bn is an upper bound of A and alpha is the least upper bound, it follows that alpha is less than or equal to every Bn. Therefore, alpha is greater than every An and less than every Bn, ensuring that it belongs to every interval in the sequence. This concludes our proof that the real numbers satisfy the nested interval property. Since the nested interval property helps us identify wholes, it is one of the fundamental properties of the real numbers. In fact, we can use it to prove that the real numbers are uncountable. To do so, assume for the sake of contradiction that there is an enumeration of the real numbers R1, R2, R3, and so on. Let's consider the following recursive construction of nested intervals. Let I0 be an arbitrary non-empty closed interval. Assuming that In has been chosen, pick a non-empty interval In plus 1 contained in In and such that Rn plus 1 is not an element of In plus 1. From the construction, we conclude that In does not contain any of the reals R1, R2 up to Rn. But since, by assumption, the enumeration contained all the real numbers, we conclude that the intersection of the In is empty. This contradicts the nested interval property, and therefore the enumeration cannot exist.